exponents. Okay, we're going to look at when the exponent is actually a fraction, and what that means and how that relates to rational or irrational expressions and radicals and those kinds of things. So first of all, this part right here, a to the 1 over n is equal to the nth root of a. Okay, so that's going to be our first key or our definition that we're going to use for a rational exponent. And so if we look at a couple practical examples, so if I have the square root of x, well, my index is a little 2, so that rule right there tells us that this is the same thing as x to the power of 1/2. Or if I have the cube root of x, that would be the same thing as x to the 1/3 power. Okay, so you can represent roots as fractional exponents, and by doing that, then we can now apply all those rules we learned about exponents to roots, and it allows us to do some more things than we were able to do before. The other part I want you to see is this right here, that a to the m over n is equivalent to the nth root of a to the m and the nth root of a to the power of m. So if I have x to the 5/3, the denominator of that fraction is the index or the root, and the numerator is the power of x. So this would be x to the 5th. And you can either put that power on the inside, or you could take the 3rd root of x first and put the power on the outside. Those would all be equivalent to each other. And the difference between the two is the order of operations. So on the cube root of x to the 5th, you take the 5th root of x first and then the cube root second. And that's the same thing as taking the cube root of x first and raising it to the 5th power second. And sometimes we'll want one, sometimes we'll want the other. This depends on what we're looking at. So this is true. This is true when we're working with when n and m are integers. M is negative or it could be positive. A can't be 0, and so on. Okay, so let's take a look at some examples. So 64 to the 1/3 power. There's a couple ways to do this. So one way is to just work with the exponents. And to do that, you want to know, well, 64 is the same thing as 4 to the 3rd power. So you could change that to 4 to the 3rd power. We still have the 1/3 out here. And if you have an exponent of an exponent, there's a rule that you've learned. Let me give you something without a fraction. Say you had x squared to the 5th power. What would that equal? In this case, it's x to the 10th. If you have x to the second, if you have one base, which is x, and an exponent of an exponent, that's the case where you're going to multiply them together. Because what that means is you have 5x squareds, right? And if you have this case, that's when you add them. So 2 plus 2 plus 2 and so on is going to be 10. You get the same answer. But the shorthand is x squared to the 5th. Just multiply the 2 and the 5 to get the 10. Okay, so that's the case we're working with now. We have 4 to the 3rd to the 1/3, and so we want to multiply the 3 and the 1/3 together. So what is 3 times 1/3? Three times 1/3. It's 1, right? You get 3 over 3, which reduces to 1. And so that's just 4. Okay. So that's one way to go, and that's just working with the exponents. Another way is to relate it back to something that we know. So what does the 1/3 power mean? That means the cube root of 64. And that's what we've been working with. You know, we're more familiar with the cube root form. And the cube root of 64, well, 64 is 4 times 4 times 4. We're looking for a set of 3 things, and so we end up with an answer of 4. Okay, both are acceptable. Second problem here. We got -2 to the 2/5. This box should be multiplication sign, times another -2 to the 3/5. So the base is the same, -2 and -2. And here, if we're working with exponents, how do you multiply two things together with exponents that have the same base? What do you do to the exponents? You add them. So that's what we can do here. So this is -2 to the 2/5 plus 3/5. We add those exponents. And 2/5 plus 3/5 are fractions, and we can add fractions when the denominators match. In this case, they do. So we get -2 to the 2 plus 3, which is 5/5, which reduces to 1. So we're just going to get -2 as an answer. Okay. So that's just working with the exponents. The other route is to bring this back down to roots. So how can we rewrite -2 to the 2/5 in terms of a root? What would the root be? It would be square root, third root, be a fifth root, because 5 is the denominator of that fraction. So the fifth root of -2 squared. Okay, that's what that means. And the second one, so this times the fifth root of -2 to the 3rd power. So I have two of the -2's underneath the first fifth root and 3 of the -2's underneath the second fifth root. So if I multiply these together, I'm going to get fifth root of -2 to the what power? How many -2's will I end up with? 5. 2 plus 3. And I'm looking for a set of 5 things. Well, I have 5 -2's, and so my answer is going to be -2. Okay. So 2 different routes again. You can take either route as long as you get to the right answer. Okay. Sometimes one route will be better than the other, and so I'm showing you both so you get a feel for both. And some problems you'll want to go one way, some you'll learn to go the other way. So 11 to the 1/2. What's the answer to that one? 11. Good. How'd you do it? Okay, so you're working with the exponents. So you add, so you get 11 to the 1/2 plus 1/2, which is 11 to the 2 over 2, which is 11 to the 1st power, or just 11. Good. Can you see how it would work the other way? What's 11 to the 1/2 written as a root? Square root of 11 times the square root of 11 is 11. Okay? Okay. So, how about 3 to the 1/2 and 12 to the 1/2? The bases don't match in this case. Can I add the 1/2 plus 1/2? No. You have to have matching bases to work with those rules of exponents. So here we don't have the matching bases, so we can't handle it like we did with the others. So we're going to have to now convert it when the bases don't match. Convert it back to fractional square roots in this case. So this is the square root of 3, square root of 12, and when you multiply those together, you get square root of 36, which is 6. Try the next one, negative 27 to the 4/3 power. Okay, so on this one, there's a couple ways to do this. One is to realize that if you work with exponents alone, you can change negative 27 to, can you think of 27 as a power of something? What? 3 to the power of 3. So negative 27 is negative 3 to the power of 3, right? And it still has the 4/3 power on the outside. And so now what we can do is we changed our base from negative 27 to negative 3, and we have two exponents that belong to that one base. So in this case, what do we do with those exponents? Do we add them or multiply them? Multiply them. So what is 4/3 times 3? Well, when you multiply it, you get 12 over 3, right? Which is 4. And what's negative 3 to the 4th power? Well, negative 3 times negative 3 is 9, and 9 times 9 is 81. Positive or negative? Should be positive because it's the 4th power, even power. Okay. So that's one route. Okay. Another way to go about this, probably sometimes it's hard to come up with that first step. Oh, that's negative 3 to the 3rd, and to see that until you're used to doing this. So another way to do this is to rewrite this to a root. So this is the cube root of negative 27 to the 4th power. And as written here, this is going to be tough to do because I don't want to take the 4th power of negative 27 first and then take the cube root of that. That's going to be a really big number, right? But that's, if you go back up to this rule here, there's another form. We can change it to the nth root of a first and then take the power of m. And so that's what we're going to want to do here. So this is the same thing as the cube root of negative 27 first, and then take the fourth power of whatever you end up getting. So that's going to be negative 3 to the 4th power, which is 81. Okay. Both work. Okay, this next one, we don't even have a fractional exponent. We just have exponents that are radicals, right? So what do we do? How do we solve this one? What are we going to do? Multiply the two square roots of 3, and you end up with 5 to the 3rd power, which is 5 times 5 times 5? 125. Okay. So the instructions on the next part is to rewrite each of these in radical form. So we've kind of, with the problems above, we've seen going back and forth with radicals. So w to the 5/8 would be what in radical form? What's the root? 8th root of w to the power of 5, and that's it. Done. Okay. We need to, on this next one, t to the negative 2/3, we need to remember something about exponents. And that is, we can't end with a negative exponent. We always got to get rid of those negative exponents. You got to remember also what that means. Like if I have x to the negative 1 power, do you remember how to get rid of that negative exponent? Or what that means? So it deals with a fraction. This is actually equal to 1 over x. Or if I have x to the negative 2, that would be 1 over x squared. So you take whatever that is, that expression, put it in the denominator of the fraction, and get rid of the negative exponent. Okay, so here we have t to the negative 2/3. So we're going to rewrite that as 1 over t to the positive 2/3. Okay, try to finish this now. We have to change it to radical form. And remember about radicals and denominators. Can't end with a denominator that's radical. So try to finish it to where it's going to be in radical form and it follows all the rules we've been learning. Okay, so we first need to change that t to the 2/3 to the cube root of t squared. We can't stop there because we need to rationalize that denominator. So we multiply by what? The cube root of t. We already have two t's underneath the cube root. We need one more to make a set of 3. But we want to multiply by 1, so we're going to multiply by the cube root of t over the cube root of t, which has the value of 1. And so when we multiply the first fraction by the second fraction, we end up with the cube root of t over the cube root of t cubed. And the cube root of t cubed is just t, so cube root of t over t. If you have a decimal like this y to the 2.6, change it to a fraction, because that's what we're working with, fractional exponents. And the decimal doesn't make as much sense when you're working with this. So to change a decimal to a fraction, not a big thing. If you have one decimal, you just drop the decimal and divide by 10. If you have two decimals, you drop the decimal and divide by 100. 3 decimals, drop the decimal, divide by 1,000. So like 2.6 is 26 over 10. Or 2.23 would be 223 over 100. And so on. And then after you get that, reduce it if it reduces. Okay. So here we get y to the 26 over 10 to start with, and then reduce it to 13 over 5. And then go ahead and do what we're asked to do here. We're asked to rewrite it in radical form. So this is a 5th root of y to the 13th power. But we shouldn't stop there. Why not? We can simplify it more. We got 13 y's underneath the 5th root, right? And we're looking for sets of 5. So we can get some sets of 5 out of the 13, right? How many, if we listed those y's in a row, got 13 of them, how many sets of 5 y's would we get? So the y squared. And then how many would be remaining? And so y squared times the 5th root of y cubed, what we're after. So remember what we've learned already, and we need to apply that to this. Okay. Try the next 3. We're going the other direction. It says to write each expression in exponential form. Do all 3 of those. Put them in exponential form. Okay, so I saw a lot of people put x to the 3/4 on this first one, which is good. And 10 to the 1/2, which is also correct. And then here, 2ab should remain at first in the parentheses, and then you 12 over 4 power. And then reduce that power, 12 over 4 to 3. So it's 2ab still in parentheses to the third power. And then everything in the parentheses gets raised to the third power. So 2 to the third power is 8, a to the third power, and b to the third power. So 8a cubed, b cubed is what we're after on that one. Okay. So fractional exponents, this is what we mean by working with fractional exponents and how they're related to radicals. Here is in our notes we have a reference to some of the properties and rules of exponents that you may have forgotten or may need a refresher with. So, and next to them you have an example with fractional exponents that you can refer to. So if you're working through something, you're like, I forget which rule I should use or how to apply that rule, this is a good place to look, okay? So next, we're asked to write each expression in simplest form. And we have the square root of 3 times the 4th root of 3. We saw stuff like that in the second section. And what did we do at that time? What's that? What did you say? We just said that's it, right? That's as much as we can go. We say, okay, that's our answer. But I did tell you, hey, there's a lesson coming where we're going to be able to handle something like that, and that's today. Okay. So if you leave it in radical form, that's really as far as we can go. But now we can change it out of radical form into fractional exponent form. And so this square root of 3 becomes 3 to the 1/2 power. 4th root of 3 becomes 3 to the 1/4 power. So now we can view it a different way. The base is the same. We got exponents. We can multiply this thing together by doing what to the exponents? Adding. Okay. So this is 3 to the 1/2 plus 1/4. Okay. So 3 to the 1/2 plus 1/4. We are working with fractions. We need a common denominator, which will be 4. So change that 1/2 to 2/4 by multiplying the numerator and denominator by 2. And we end up with 3 to the 3/4. And that could be your answer. Or you can change it back to radical form and get 4th root of 3 cubed, which is the 4th root of 27. Okay. Try the next two. And write the answers for the next two, write the answers in both forms like I did. So put one answer in fractional exponent form, put one in root form. So just to get used to both forms. All right, x to the 4/3 times x to the 5/6. The way to handle this is to add those exponents, right? So 4/3 plus 5/6. Because if we went back into root form, we'd have a cube root and a 6th root, and we need to have the same root, right? But same idea here, we need a common denominator, and the denominator is the root. So we need to change that 4/3, multiply top and bottom by 2 and get 8/6. And 8/6 plus 5/6 is 13/6. And so that can be your answer in fractional exponent form. Or if we change it now to a radical form, we get the 6th root of x to the 13th. So we have 13 x's underneath the sixth root. So we're looking for groups of 6. And how many groups do we have? 2. So x squared with the sixth root of how many remaining? Just 1. So either of those are equivalent to each other in different forms. Okay. And then the 5 times x to the 3/4 to the negative first power. What's the power of 5? Is it 3/4? Does the 3/4 belong to the 5 and the x, or just to the x? Just to the x. So the power of 5 is a 1. Okay, so that's important to know. So there's a couple ways you could have handled this. You could have multiplied both of these by -1, or just said, well, that -1 means I'm going to move everything to the bottom of the fraction. Make the 5 times x to the 3/4 the denominator. So either way, you'd end up here. Okay. So is that it? We stop there? Why can't I stop there? What's wrong with that as a final answer? What's that? Good. Although it may not look like it, but the denominator has a fourth root in it, right? Because x to the 3/4 means the fourth root of something, and you can't end up with a radical in the denominator. We got to rationalize that denominator. So there's 2 ways to handle this. We can work with just the exponents and think, well, that x is fine. I just don't want a fraction there for an exponent. So I'm going to decide what I want to multiply that x to the 3/4 with x to some power. What would I like? And I get to pick any power I'd want to. What would I want to multiply x to the 3/4 with? X to the what? To get rid of that fraction. How about 1/4? Because when I multiply those together, I actually add the 3/4 and the 1/4, which is going to make 1, 4/4, 1, and that will get rid of my fraction. But I have to multiply this fraction by 1, so I'm gonna multiply by x to the 1/4 over x to the 1/4. And I end up with x to the 1/4 over 5 times x to the 4/4. But we can get rid of that fraction. And x to the 1/4 over 5 times x. So that's how you can handle it without even going back to radical form. Other option is not to do that and to change this to 1 over 5 fourth root of x cubed. Sorry. And then you would think, like we've been doing before, what do we need to multiply that by? About fourth root of x over fourth root of x, which, by the way, is the same thing as x to the 1/4 power. And so when we do that, we end up with the fourth root of x over 5 times the fourth root of x to the 4th, which is the fourth root of x over 5 times x, which is exactly what we have in the other form. Okay, so now division. Let me bring your attention to the division property with exponents. Okay, when you have the bases are the same, so here we have base a, we have a to the m over a to the n. You can divide by keeping the base the same and subtracting the exponents. Okay, and so we're going to use that rule on this next one. Okay. Can I got 3 x's in the numerator, 2 x's in the denominator. Can I cancel out or divide out x squared? Why not? You got a square root and a cube root. And if your roots don't match, you have to get out of the root form. You have to get into the fractional exponent form. Okay, there's no way around that. So the numerator becomes x to what power? 3/2. And the denominator is x to the 2/3. And that rule we just went over says, hey, if the bases match and you're dividing, then you keep the base the same and you subtract the exponents. And you have to use the numerator exponent minus the denominator exponent. So 3/2 minus 2/3. Got to get that common denominator, which will be 6 in this case. So the first fraction, you're multiplying numerator and denominator by 3. You get 9/6. Second fraction, you multiply numerator and denominator by 2 and get 4/6. And now we can subtract and get x to the 5/6, which is the same thing as the 6th root of x to the 5th power. So the next one is another division problem just written in a different form. So it's very similar to what we just did. I want you to do that one. And do the second one, 50x to the 16 over 18y to the 8th, all to the 1/2 power. See if you can simplify that one as well. Okay, y to the 3/5 divided by y to the 4/10. We know with division, if the bases are the same, you subtract the exponents. The numerator for the first fraction exponent minus the exponent of the second fraction. We want a common denominator, and so we have two options here. We can change the 3/5 or we can reduce the 4/10. Because the 4/10 you can divide out of 2 and end up with a 5 as the denominator. And so I'm going to reduce, get y to the 3/5 minus 2/5. And then when you subtract, you end up with y to the 1/5 power. Or the 5th root of y. Okay. How about this next one? Did anybody run into difficulties on this next one? So? It just depends how you handle it. Remember when we worked with the other fractions, what was the first thing I told you to do? If you could. There's like 3 different steps that we were looking at. It was like on the third lesson, or maybe the second lesson actually. It's been a while. Anybody remember when you're working with the fractions, what was the first thing I told you to try? Reduce. Can you reduce anything here? 50 and 18, huh? Well, the 50 and the 18, if you divide them by 2, you end up with 25 and 9, which is going to be very helpful for us because what does the 1/2 power mean? Square root. And if you left it 50 and 18, you'd be like, I can't take the square root of 50. I can't take the square root of 18, right? But if you reduced it, you got 25 and 9, and those are perfect squares, easier to work with. And so square root of 25 is 5, square root of 9 is 3. How about the square root of x to the 16? Well, think you got 16 x's. How many pairs of 16? You can make 8 pairs of x's, right? If you had 16 of them. And if we have y to the power of 8, what's the square root of that? And there's our answer. And we don't have two forms of this answer because there's no fractional exponents in this answer. Okay. All right, our last one. Again, it's a division problem, but we have more than one base we're working with here. And so we just work one base at a time. So we have the x to the 1/5 over the x to the 1/2. So the base is x, and subtract those exponents, times, now we have the second base is y, and the numerator is negative 1/5 minus the denominator is negative 1/2. And careful, you have a double negative here. And then get a common denominator and subtract. So our common denominator would be 10. First fraction becomes 2/10. And second fraction becomes 5 over 10. And negative 2/10. Double negative makes it positive 5 over 10. Go ahead and finish that. And remember, your answer can't have negative exponents. Your answer can't have radicals in the denominator. Try to get to the answer of this. So when we subtract the exponents for the base x, we end up with x to the negative 3/10. And for y, we end up with y to the positive 3 over 10, which we can't stop there because the x has a negative exponent. And so what we do is we now put it in a fraction. The numerator stays y to the 3 over 10. The denominator becomes x to the 3 over 10. We're moving that to the denominator and making the exponent positive. We can't stop there because when you have a fractional exponent, that denominator represents a radical. We can't have radicals in the denominator of a fraction. And so what would we like to multiply by? X to the what power? 7 over 10. Good. So we multiply by x to the 7 over 10 divided by x to the 7 over 10, which is just 1, but it's going to help us do what we're wanting to do here. And we end up with y to the 3 over 10 times x to the 7 over 10 all over x to the 10 over 10, because we add the 3 and the 7. And I'm just going to switch it around. I like to put it alphabetically. So x first, y second. It's okay if you didn't do that, though. All over x. And that's the answer we're looking for. Or you could write the 10th root x to the 7, y to the 3rd over x. That would be the equivalent answer in the other form. Okay, before we leave this, I have a question for you. Which one's larger? The square root of 3 or the 8th root of 81? Without a calculator, which value is larger? What's that? They're equal? You don't know? You're just thinking it might be a trick question. Which one's bigger? We can answer this now. Square root of 3 or the 8th root of 81 without a calculator. Which one's larger? Okay, so this is 3 to the 1/2. This is the 8th root of 3 to the 4th, which is the same thing as 3 to the 4/8, which is the same thing as 3 to the 1/2 power. So they are equal. Okay. Matt just knew something about Mr. Marsh that he can answer that.